Okay. All right, so let's get started. Okay, so today we're going to talk a little bit, we're going to move on and talk about 4.5, which deals with the chain rule. And of course, in many variables. This is one of those points in the course where I'm going to diverge a little bit from the book, online book. Of course, everything I say, you can find versions of it in the book. But, you know, this is, the chain rule, I think, is really best presented as a nice generalization of the one you're familiar with. And so I'd like to kind of give that idea, because otherwise the formulas, they look a little bit strange, I think, in many variables. They don't seem to make quite as much sense as they should if you just take them as formulas without the background. So let's recall what is the chain rule in one variable. So we have two functions. We'll have a function, I'm going to just draw a schematic function from R to R. Okay. Let's say this is F, and then we have a function from R to R again, G. So it takes inputs real numbers and outputs real numbers, each of these functions, and then we can compose them. I'll do the more, switch the order here, do the more common. There's a little bit of a reversal of order of F composed with G. And then, so this is just a composition of functions. Let's assume everything is differentiable. What you're allowed to do is take the derivatives of everything in sight. And so the point is that there is a chain rule is a formula that relates the different derivatives. So if I take F composed with G and take its derivative at a point, say A, right? And this is equal to F prime G of A times G prime at A. And the way to think of that is to think that the derivative, there's sort of a commutativity of derivatives. So if we have a point A here, A is in, this is the symbol for element of, but okay. So there's some element A in here, and this is sent to its value, G of A. Then you can say, okay, well, if I start here and I take the derivative, then I get this function, which I can think of as multiplying by the derivative. And then if I start here, this point, take the derivative of F at this point, then I can think of multiplying by the derivative there. Or I can just take the derivative of the composition, F composed with G, at A. And then the idea is that this equation says that if you go through these steps, it's the same as going through this step once you take the derivative. That's one variable chain rule. It's a recasting of this equation in terms of compositions of functions and their derivatives. And the reason I'm doing it is not just to talk, but it is to say that the generalization to higher dimensions is precisely this kind of equation. Although if you write it out in ordinary ways, it doesn't look like it. So let me explain. In order to explain, I need to say something about matrix multiplication. So it's not quite required that we know how to multiply matrices in this class, but I think, well, how many people, by a raise of hands, know how to multiply some matrices? If I give you some matrices. All right, so there's a few people, maybe not so much. That's okay, it's not a prerequisite here. But I want to say, this is not any more difficult than taking dot products, all right? So if you know how to take dot products, multiplying matrices is just like taking a lot of dot products. So let me give you some notation. And then we'll do a couple of computational examples. So now what is a matrix? So a matrix is, you know, a film with Keanu Reeves, I guess, but it's also like, right, a bunch of entries, a bunch of numbers, if you think of a matrix with real numbers. So I'm going to say A is an M by N matrix. This means that it has M rows and N columns. So it's like a table of numbers, if you want to think of it that way. And usually we'll write the entries in that table as A sub ij, where I denotes the row number and J denotes the column number. So for example, I could have a matrix like this, 2, 1, minus 1, 1, 0, pi, right? Got a matrix of numbers. And if I wanted to know if this is my A, well, first of all, this is a 2 by 3 matrix. It's an example. And if I wanted to say, what is a 2, 2? Well, that's the column, or that's the entry in the second row in the second column. So here's the second row, here's the second column. It's this entry here. So it's 0. Okay, makes sense? So if you take some more math courses, I would really recommend everyone take some form of a linear algebra course at some point. There are going to be far more applications of linear algebra in whatever you do than probably any other subject in math. I would say that. Okay, so this is kind of a really basic linear algebra, just matrices and so on. All right, so now let's suppose I have another matrix. So if B is an n by p matrix, we can form the product which I'll call C, A times B. Now, okay, so I need some entries here. I'll give this the entries B sub JK. So that's same idea. J is the row, K is the column. And I'm saying that we can form a product A times B. This will also be a matrix. So this is a product matrix. Now, I want people that are not familiar with this to make a mental note. I can form this product here only because the number of columns of A is equal to the number of rows of B. If those two numbers are not equal, then there's no such notion, at least not a standard notion. Okay. So how do we do it? Well, we have a formula. So this is going to have entries Ci, K, and I'll give the equation for Cik, and then we'll just do it and you'll see it's not very hard. So this is just the sum from j equaling 1 to n of Aij times Bjk. Take the products and you sum up, just like a dot product. Okay, so don't memorize this formula. The best way of remembering it is just doing a few examples, maybe 2 or 3 examples, and you'll never forget it. So here's some examples. So we could take the matrix product. Let's say I have, I don't know, 1, 2, 3. Space this a little better. 1, 0, minus 1. Then I have the matrix, let's say 1, 0, 1, minus 1. Okay. So what I do when you multiply matrices is I'm going to say what this is. So first of all, I should have said it before, but this product is going to be an M by P matrix. So the question? Sound like a chair or something. So if you want the number of rows in here, it's equal to the number of rows of A. If you want the number of columns, it's equal to the number of columns of B. So in this particular case, we're going to have a 2 by 2 matrix. We get a 2 by 2 matrix. And so I want to know, let's say, the 1, 1 entry of this 2 by 2 matrix. So what I do is I take the first row of the first matrix and the first column of the second matrix. And I essentially take their dot product. So I'll take 1 times 1 plus 2 times 0 plus 3 times 1. So that's 1 plus 3, which is 4. If I want to find the entry in the first row, second column, what I'll do is I'll take the first row here and the second column here and take a dot product essentially. Right? So I'll take 1 times -1 plus 2 times -1 plus 3 times 2. So that's 6 minus 3, that's 3. Similarly, if I want to look at these last two entries here and here, I want to take the second row, first column, that's 1 plus 0 minus 1, that's going to be 0. And then I want to take the second row and the second column, and I'll get -1 plus 0 minus 2, so that's -3. So I could do this all day long and no one would learn anything. The way that, I mean, if you haven't done this before, again, the best way to learn this is just do a few examples. You're going to feel fine after that. It won't be, but if you don't actually do those, it won't be as easy to remember. Okay. Great. So we have, and this is just a brief refresher on what matrix multiplication is. And I'm not going to belabor the point. So what I'd like to do now is actually kind of go from a linear setup, which is, this is sort of linear algebra, multiplying matrices, to a nonlinear setup, which is what we're really focused on, thinking of functions in several variables. So let's suppose we have a function of several variables. Our function will be defined, we'll just say on Rn, but we can think of it as a domain, and it's going to be take values in Rm. Okay. So as I said, I'm diverging from the book a little, but we're going to scale back and we'll do some examples in 2 and 3 variables and 1 variable. So don't worry too much, but I want to get the general setting set up. So what is this vector value? So this is sort of a vector valued functions in several variables. And it'll take inputs, input variables x1 through xn, and I'll give myself m scalar valued functions. f1 of x1 through xn, f2, x1 through xn, all the way to the last one, f sub m, x1 through xn. This is sort of the most general function we could consider. Uh-oh. What did that happen? Oh, wow. It's very sensitive. Sorry. Okay. Now, we're going to, so we have a notion that we defined last lecture of differentiability of scalar value functions. Okay, it was this complicated limit, which basically said the linear approximation is a good approximation of first order. That's essentially the idea of it. So what does it mean for a function like this f to be differentiable? It's not scalar valued. It takes values in some vector space, Rm. Well, we'll say that f is differentiable if each of these functions is differentiable. F sub I, I'll just say f sub I is differentiable.
So we have a notion for f sub I. And this should be true for each, for all I, between 1 and m. So I mention that because the chain rule is not true if you just take functions whose partial derivatives exist. Okay. It's only true for differentiable functions. All right. So in this case, we can talk about the derivative of f. It's also called the total derivative, but it assembles all of the information of the first partials into one big guy matrix. And what is it? It's a matrix. df, this is also sometimes, although I don't like the notation, but some people write df, lowercase df. This is not what I would write, but it's used sometimes. What do? You take each of these coordinates and you take their partial derivatives, the first partials. So we'll take the first column to be all of the first partials of the first guy. Sorry. Pardon me, first row. Let me skip those mixed up. First row, this is going to be F2. So we have n variables, we can take n different partials, and that will form our first row. Okay. And then similarly, we can do the same thing with the second row. We can do it all the way down until we get to the last row. And we have m guys here, m rows. Okay, so this is an m by n matrix of functions. Now what's in the matrix are actual functions, they're partial derivatives. But if you evaluate at a point, you get a matrix of numbers. This is the total derivative. It's really, I really like this. Let me tell you why I really like this. We can get lost in the weeds, right, with a lot of things. But if we assemble things correctly, right, I mean, there's a lot of partial derivatives. We can form all sorts of combinations of them. But if we assemble them correctly, we have a single notion of the derivative of a multivariable function. And then a lot of the things that we want to consider are really about this single total derivative. Even though it's complicated, it's correctly assembled, is what I want to say. Okay. All right, so what do we want to do to this? Well, we want to state the chain rule. But before we get there, let's give ourselves an example. This is an example that will come up again later on when we do change of variables formulas for integration. So this does come up later on, although we don't really talk too much about the total. Here's an example. Let's make a computation of the total. So consider, I'll call it P. Whoa, yikes, very temperamental. Okay, so P is going to be a function. I'm going to say what it's a function on. It's a function on this interval, half open interval, across the interval 0 to 2 pi. And it lands in R2. What does P do? So first of all, what is this business? Well, this is a subset of R2, and we can see what it is, right? We take the half open interval. This goes from 0 to infinity. And then we cross it with this interval, this finite interval here. Oops, whoa. So we just cross it and we get this guy. So this is the domain. And it's contained in R2. It's the domain of the function. I'm going to give myself variables, coordinates here. They're going to be R and theta. And P of R theta is going to equal R cosine theta, R sine theta. P is the function that changes coordinates from Cartesian coordinates to polar coordinates. It's a function. Let's take its total derivative. It's differential. Let's take its total derivative. So this guy here is going to be our, say, P1 of R theta. This is going to be P2 of R theta. So if I want the derivative of P, well, I've got two variables and I've got two functions. So it's going to be a 2 by 2 matrix. And we can write it out sort of abstractly first. We do that. So this is going to be del P1. Of course, these x1, x2, and so on, you can label your variables how you want. Del P1, del R, del P1, del theta. And then the second row is going to be del P2, del R, del P2, del theta. We can actually compute these. The partial of P1 with respect to R is just cosine theta. The partial of P1 with respect to theta is going to be negative R sine theta. And partial of P2 with respect to R is going to be sine theta. While the partial with respect to P2 with respect to, of P2 with respect to theta is going to be R cosine. This is the total derivative of this function P. This total derivative is used very frequently when you want to change, let's say you have a function and you know all of its derivatives in terms of Cartesian coordinates, and you want to transfer them to derivatives with respect to polar coordinates. This is what you can use. We'll see that in a moment. If you're integrating over Cartesian, you want to integrate instead of over polar coordinates, you use this matrix, as we'll see next section, to understand how you change those integrals. So this total derivative does enter into the mix quite a bit. So now, however, I want to talk about the main player, the main subject today, generalized chaining. Okay. So let's let G, we'll use the same kind of notation that we had before. It's going to be a function from Rn to Rm, be differentiable at a point A. And now A is a point A1, I mean, it's a point in Rn, so it's got coordinates. And F is also going to be differentiable, but it's going to go from Rm to Rp. It's also differentiable at the value that we get when we apply G to A. So at G of A, which you can write down as M different points if you want, but I won't worry about it. Then F composed with G, we can compose these functions, right? We can start with G. We'll take Rn to Rm, and Rm is our domain here. So then we can hit whatever we get with F. That's a function. We'll assume, of course, I mean, I said these are differentiable at these points, so we don't need to take all of Rn or all of Rm. We could have smaller domains, but G of A should be in the domain of F. But anyway, we can look at F composed with G, say it is, based on these assumptions, it is differentiable at A as well. And furthermore, the big deal is that its derivative at A. So let's say we evaluate this at A. So this means, remember what I said before, this is a derivative of functions. I'm going to evaluate each of those functions at A. So that's now a matrix of numbers. This matrix of numbers is obtained by taking the total derivative of F and evaluating it at G of A. And that's a big matrix, right? That's a P by M matrix. And we can multiply that matrix by the derivative of G at A, which is an N by M matrix. Or M by N, sorry. This guy, as I say, this is going to be P by M. This is going to be M by N. So they can be multiplied. This is the chain rule. This is a miraculous formula, like a very, very impressive formula, I think. And if you look at it, it's not just one equation, right? It's P times N equations for each of the partials of this composition. They all fit together coherently into this matrix multiplication. Okay, this is the grown-up version of the chain, I want to say. And I know it's a little petty, but I want to share it with you because I think if you look at the formulas without it, it sort of seems strange. It seems strange to where they're coming from. Who knows? But what I want to do now is I want to go to those cases, those special cases where we put in certain numbers for N, M, and P that are more explored in the book. One of the advantages, though, of course, to knowing this formula is you don't have to memorize 6 different formulas or 6 different techniques. There's only one generalized chain rule. Okay. So let's take a look. Of course, I'm not going to do the case of one variable where everything is 1. That's just the ordinary chain rule. So let's take a look at the case, say, of special cases. We'll say N equals 1, M equals 2, and P equals 1. So in this case, G is going to be what we've been thinking about as a vector valued function. So it's going to take a single variable and return two variables. So think of this path in the plane, if you want. F is going to be a scalar valued function from R2 to R. So we can write down G, say G of T, we'll give a parameter for our domain T. This is going to be X of T, Y of T. And we can write down F, say F is Z, just write down Z equals F of XY. Now, what is the composition? The composition is, say, z of t is going to be f of x of t, y of t. And so if I compose these two, I'm starting with G. I'm going to go from reals to the plane and then back to reals. So if I compose them, I have a single variable function. So if I'm talking about derivatives, single variable functions, I just have a derivative, ordinary old derivative. So if I take d, capital D of f goes with g, this is just our ordinary derivative, dz dt. That's it. So if you want, you could write it as a 1-by-1 matrix, but it's just 1-by-1 matrices. You don't usually put the brackets around. On the other hand, what are the derivatives of g and of f? Total derivatives. dg has two functions, so we're going to get a 2-by-1 and has one variable in the domain. So we're going to have a 2-by-1 matrix for the total derivative. So we'll get a dx dt. When you're talking about partials and there's only one variable, you just take the ordinary derivative, dy dt. So you get a matrix of two functions. df, total derivative of f, what is that? That's going to be a 1-by-2 matrix. You're going to get del f, del x, del f, del y. So what is our generalized chain rule? Now that we have everything, all of the ingredients on the board, well, it says that this, evaluated at a point, and we can evaluate at any point in time here, right, is going to equal the matrix product of these two. So we get dz dt is equal to df, which is this guy. And this should be evaluated at x of t. Oops, sorry, this should be y. This should be evaluated at g of t, not at x of t, at g of t. Right? But we're going to multiply these two. We get dx dt, dy dt. And when we look at it, of course, we know how to now multiply matrices. We'll get a d. So sometimes they'll write f as z because they've got this equation. So let me do that here. Sorry, let me do that here. Just to agree with the notation in the book. They think of z as the function. That's fine. It changes. All right, so then what do you get? You get del z del x dx dt plus del z del y dy dt. Okay, so this is in this case, this is the chain rule for these dimensions. And they spend a good 3 or 4 pages in the book talking about this particular version. Now, I want to say, if you went from one variable calc, in my view, and you looked at this chain rule, it would seem very strange, mostly because of the sum. Right? It's kind of odd that you're summing up these things. But if you think of it in terms of the usual chain rule, but now you're replacing multiplication of derivatives with multiplications of matrices, this is very reasonable as an expansion. Okay. Of course, there's a proof to all of this, but I don't want to trouble you guys with that. All right. So a lot of generalities. I know it's sort of notation heavy and conceptual heavy. So let's do an actual computation here. So here's a problem. So let's z equal xy minus y squared. And let's take x of t be cosine of t, where y of t will take to be sine of t. So the idea is we've got some function on 2 dimensions. It's given by xy minus y squared, but we're not really interested in the rate of change of that function as we kind of move in 2-dimensional space, but rather as we move along the circle. So what we're going to do is compose these things and take a derivative and check chain rule works to calculate the change of z as I move along the circle. Change of z with respect to t. So the problem will be calculate dz dt. Using chain, I will say using chain. I mean, in some of these cases, it's not hard just to go ahead and put in the functions and evaluate, compose the functions and go from that standpoint. However, the chain rule can be used in a lot of different contexts where you don't have all the information you need to do that. All right, so let's do this with the chain rule. So we're going to calculate all of these derivatives. And then we can use them to calculate this derivative. So we calculate del x del z, or sorry, pardon me, del z del x. Del z del x is just y. Del z del y is going to be x minus 2y. Now we're going to calculate the derivatives of x and y with respect to t. Dx dt, this is minus sine of t. Dy dt is going to be cosine of t. Now, as I said, if you're going to apply this chain rule, these partial derivatives of z, you need to evaluate them at x of t, y of t. So you need to put them in terms of t. So this y is y of t, and if I want to write it as such, I just get sine of t. Right, and then this partial will be cosine of t minus 2 sine of t. Once I have everything written in terms of t, now I can use this chain rule. So now dz dt is going to equal, now I just multiply negative sine t. Questions? Everything good? Okay, negative sine t times sine t. And then I add cosine of t minus 2 sine of t times cosine of t. And we can expand out if you want. It's cosine squared minus sine squared plus, pardon me, minus 2 sine t cosine t. And for all of you that are trig literate, I don't know, right? You'll get a cosine of 2t. You remember your double angle. And if you don't, nobody will mind. All right. So this is an application of the chain. Now, as I said, you could very well verify this by putting in these functions into z and taking just the ordinary derivative. And in this case, it may even be easier to do it that way. But sometimes you don't have all of that information and you want to be able to take these derivatives implicitly. So the chain rule is necessary in those cases. Questions? Okay. All right, so let's look at another special case. Another special case. So the other special case, which again, this is used very frequently, is something like where we change coordinates, like go to polar coordinates or spherical coordinates or cylindrical coordinates. And then we have a function written in one coordinate system and we want to write it in terms of the other. Well, that's not hard to do. We've done that already in the first part of this course. However, once we start taking partial derivatives, we'd also like to know how to change the derivatives in one coordinate set of coordinates to the derivatives in the other. Like to see how rates of change can be expressed using this new coordinate system and using the calculations you make in the Cartesian setting or the other setting. So one version of that would be in case of dimension 2. So we'll take the special case, case 2, where n and m are both 2, and I'll remind us what that means, and p is 1. So we have some function g, which we think of as a change of coordinates from R2 to R2, for example, polar coordinates. And I'm writing R2 to R2, but again, this can have a domain that's smaller. It doesn't have to be all of R2. I'm just, for convenience sake, I want to just write R2. And we'll label the variables u and v, as is done in the book. And we can write out our function xuv, yuv. So rather than having these f1, f2, f3, since we have so few variables, we can give each variable a different letter. Our f will be a function from R2 to R. So this will be a scalar valued function. And we'll just, again, write this as z equaling f of xy. And again, if we look back up here, we remember what df is. df is this guy. And I'll bring that down here to remind us. However, dg becomes a slightly more complicated looking fellow, right? Here, dg is going from g is going from R2 to R2, so this should be a 2 by 2 matrix. Indeed it is. And its first row is going to be the partials of x with respect to u and v. And the second row is the partials of y with respect to u and v. And so now, if I want to, so as I said, this guy is what we've been doing, right? We've taken a function f and we've talked about linear approximations and calculating all kinds of nice things about f. And all of those computations involved, well, recently, the first partials of f with respect to x. And now what I'd like to do is I'd like to work in my uv coordinates. So what I really want is I want to look at, del z, maybe I can write this as z or f, I don't know. I'll use the book's z here. Sorry. What I really want is I want a del z, del u, del z, del b, right? I want something like that because I want to go to my uv coordinates and make all those types of computations in that coordinate system. But this is the derivative of this composition. Which means by the chain rule, we have that this is equal to this matrix times this matrix. Pardon me, I switched the order. Wrong order. This matrix. So you can write out, so you get two equations, one for each partial derivative, and you can write them out, del z, del u. This is going to be del z, del x, del u, plus del z, del y, del u. And similarly, del z, v, is going to be del z, del x, del v, plus del z, del y, del v. This is this version of the generalized chain rule. And again, it is not like, I mean, just the expression, the equation, just on its face, when you look at it, does not look like one variable calc. You have to sum these different products. And I think that throws a lot of students off when they first start working with this. And when they work on it later on as well. All right, hopefully this won't be the case for you guys. So let's do an actual computation here. Let's look at the problem, the following problem. So let's let f, or z equal f of xy, just be the product xy. And we're asked to find del z, del r, del z, del theta. In other words, you want to know what the rate of change of your function is as you radially move away from the origin. This is actually something a lot of applications you may want to know. The rate of change as you move away from some point. Or you want to know the rate of change of your function as you rotate around it. So del z, del theta. And what you do know maybe is you know the partials of this with respect to x and y. So to write the solution of this guy, well, let's calculate all of the things we need here. And let's remember, we've already done a calculation. We actually have already done all of the calculations for r and theta. So in this case, let me note here, r theta, this is uv. So we've already actually calculated this del g, or dg, which is just the matrix that we had for polar. Let's bring it. Let's use our work. I know it's a long time ago, but we can remember it. So our dg here is precisely this matrix. And our df, or dz if you want, either one, df, I'll write it, is just this matrix. We can take the derivative of f with respect to x, which is dz dx, which is y, and dz dy is x. But again, I want to write this in terms of r theta. If I'm going to use the chain rule, you do want to put in the derivative of f at g of r theta. So this is going to be r sine theta, r cosine theta. And now we have a very simple computation on our hands. We're going to calculate both at the same time, del z, del r, del z, del theta. It's just obtained by multiplying these two matrices. So let's just, interest of efficiency, just write these down this way. First, it's going to be r sine cosine theta plus r sine cosine theta, which is 2r sine theta cosine theta. Then we get negative r sine theta, sine squared theta, pardon me. And I have a square. So let me write this down as r squared. I can see, okay, so we're running out of time, but let me just write cosine squared theta minus sine squared theta. Again, I do see some double angle formula. So I'll get equals r sine 2 theta, r squared cosine 2 theta. And I can make this calculation. So this is equal to this, and this is equal to this. Get two equations. All right. So let me just say one thing before you all go. I want to present this to you because I want you to see it and I want you to understand it as best you can. I'm not going to be test heavy with this lecture. Just so do read the book and try the problems